Is it live? Okay. Hello. So, what do I say? This is the UNSW MathSoc Society. This is the 2521 2621 seminar, and just like an overview, just for this session right here, we're just gonna do an intro into complex analysis first, and then after that we'll look into limits and differentiability, and the rest of the stuff will be tomorrow, same time. So yeah, so overview 2, this is what's gonna happen next lecture. And so yeah, so just intro to complex analysis. So basic rules and ideas. I'm pretty sure you do remember what complex numbers are from 1141, 1241, but just as a small reminder, there are numbers that can be written as z equals x plus iy for some real part x, some imaginary part y, or you can write it as z equals r e to the I theta, which is the Euler form. And so, and also normal rules of addition, multiplication, subtraction, and there's also a notion of division here as well. And just an idea is that when we multiply complex numbers, like geometrically, it's scaling and rotation. So if we look at this Euler form here, if we multiply if we have is this right here, z1, if this is r1 e to the I theta 1, and z2, it's equal to r2 e to the I theta 2, we'll have their product, z1, z2, is just equal to r1 times r2 times e to the I theta 1 plus theta 2. It's not going to fit, but... So basically, yeah, the arc is additive, but the modulus is multiplicative when you multiply it. And other important ideas, we have the modulus of any complex number z is just z times its conjugate, and we have the principal argument is the argument of our complex number, which is between negative pi and pi. So I'm pretty sure you already know all of this, but anyways. So like, if you remember, one of the first things we went over was just the triangle inequality and circle inequality. So triangle inequality, we kind of know what this is if we get a triangle. So effectively what this is saying is if we have a triangle, like the sum of these two sides is it's at least the length of this side. So you can think of this as just the length of this side here, w plus z. This side here is w, this side here is z. So that's triangle inequality. Circle inequality, it's basically a rearrangement of the triangle inequality. So yeah, that's basically all there is to it. And one small example is if we have a modulus of z is greater or equal to 2, prove this inequality here. So if we're going to use triangle inequality, circle inequality, it's first thing to do, best thing to do is basically multiply these two. Multiply them out so we don't have the fractions on the denominator anymore, and it suffices to show that 15 is less or equal to z to the 4 plus 1. But we can just show this with our circle inequality, since we can split our z to the 4 plus 1 into, add absolute here. So we can split our z to the 4 plus 1 into z to the 4 minus 1. And then we know the absolute values of these. Well, we know the modulus of these, which this is at least to the 4, this is at most minus 1, and that's 15. And we get the desired inequality. So do you have any questions? All right. So, okay, so this is really this is where the definitioning part of complex analysis comes in. So first thing we defined in the lecture, we defined what a ball was. So basically a ball, what a ball is, it's just a circle with everything inside. And Okay, it's whatever. So basically this is a ball with everything inside. So when we write bz0 with epsilon, we mean that the center here is going to be z0, and in this distance, this radius is going to be our epsilon. And we also have this notion of a punctured ball, which we denote as b. We add a 0 here, I believe. And what this is saying, it's just the ball, but we exclude the center. And we also, and now with this idea of a ball, we can describe like the interior, exterior, and boundary of some like closed set. So if we have like some area here, some like glob here, we'll call this S. Then what an interior point is we can pick up any point here, no matter how close to the, how close to the border you can pick it. You can get a ball such that everything inside the ball is in S. And we can define our exterior points similarly, where we can get, for any point, we can get a ball centered that point close enough, like small enough, such that all the points are not in S. And what a boundary point is, it's basically, no matter how small our ball is, we can't get every point of the ball either completely outside or completely inside our point S. So that's basically, that's how we define interior-exterior boundary. So does that make sense? All right. And now we have a lot of definitions. So we for every point set, we have these definitions. The point's open if every point inside it, like every point in S is an interior point. So what that looks like visually is, it means if we, let's say we have our blob S here again, it means that, wait, okay. Oh, sorry. It's our blob here S. It means we don't have any boundary points in S, basically. And what closed means is, instead of having no boundary points, we have all our boundary points. And the closure of any set is like the set plus all its boundary points. So whatchamacallit, if we have just some open circle here with like dotted around here, the closure of this set would just be the circle with the perimeter as well. And okay, what is bounded? So bounded just means that you don't go infinitely far. For example, okay, let's rub this out. So if it's bounded, it means we can just pick a big circle that would encapsulate our set. So if we had some set here, we can pick a big circle that contains the entire set. So what an unbounded set would look like, for example, is the set here, where we take everything to the right of this line. And that would be unbounded because, like, no matter how big we pick our circle, there will always be some point very, very far to the right that is outside our circle. Compact is just if it's closed and bounded. And a region is basically in between open and closed. So it's an open set with some amount of its boundary points. Maybe all, maybe none. So that's how we define it. And let's scroll. So now we introduce this idea of arcs. So I'm pretty sure the lecturer said it's a lot easier to deal with arcs when they're polygonal, which is basically just like lots of lines rather than curves, because lines are a lot easier to deal with than curves we don't necessarily know the properties of. So a polygonal path is just some path from one point to another, and it's composed of lots of different line segments. And a closed polygonal path is going to be any polygonal path that that just ends up back at its starting point. And anything that's simple is anything that just doesn't cross over with itself. So for example, this here, starting from here, would be a simple path, whereas this thing here would not be a simple path. This is no, this is yes. So from here, we define polygonally path connected, simply path connected, and a domain. So it's polygonally path connected. So a set is polygonally path connected if for any 2 points in our set, we can create a polygonal path that goes from one point to the other. For example, if we pick this annulus here, if we have some A here and some B here, we can always pick some polygonal path. We can go like this. We can go around the center, and we can still go from A to B. Whereas if we have Whereas if we have some set like this, which is just both of these, if we pick some A here and some B here, we can't get a path between them that's contained in the set. Right? So we understand that? And so what simply polygonally connected is, it's kind of like an upgrade to our polygonally connected path. Polygonally path connected set. So it means that if we go back to our annulus here, we need like the interior of every polygonally closed arc in S to be a subset of S. So what that means is, if we take this arc, this closed path here, starting ending at A, we know that like not everything on the inside is going to be an S. We have this hole here, so we can see that this isn't simply polygonally connected. Whereas if we just take just a circle here, no matter which path we take, it's gonna contain everything. So basically what this means is that our set, if it has no holes, it's going to be simply polygonally connected. And domain is just a polygonally path, if it's polygonally path connected and it's also open. So that makes sense? All right. Oh, sorry. So here's just an example. We want to determine if the following sets are open, closed, bounded, compact, whatever, right? So here are our sets here. So first things first, I believe the lecturer often says this. It's draw our sets. What do our sets look like? First, let's look at S1 here. So S1 is this set here. It's a circle centered at 0, and it doesn't contain the boundary points, but it's everything inside. And this should be I, this should be negative I, this is 1, minus 1. So that's what our S1 looks like. So is it open, closed, bound, compact, whatever. We can see that it kind of just doesn't contain its boundaries, so it's going to be open. So is S1 open or closed? It's going to be open. Is it bounded? Well, we can just pick a circle bigger than it. We can just, for example, pick a circle of radius 2 here. And then our entire set S1 is going to be contained in this circle. So that means it's going to be bounded. So we take this here. Is it compact? Well, it's not closed, so it can't be compact. So it's not compact. Is it polygonally path connected? Is it simply path connected? We can kind of see that, any 2 points, we can just draw a line and wow, it's polygonally path connected. And simply path connected, we can see there's no holes, so it's going to be both. And is it a region? What is a region again? It's just polygonally path connected and open. So that means since it's open, since it's polygonally path connected, it's going to be a region. So do you understand that? All right. And we can continue on. We'll just do, we'll do S2 and S3. We'll skip S4. So S2, what does S2 look like? Oop. S2 is just a region, including this 0, but not including this 1. And it's everything in between here. So now our question is this open, is this closed? Well, we can see it doesn't contain all its boundary points because some of these boundary points here aren't, it's just not in our set S2. But also, we have some boundary points here which are in S2. So it can be open, it can be closed, so it's neither. So we have none. Is it bounded? Well, we can't really contain it in a circle because this rectangle thing goes infinitely far. So we can just kind of see it's not bounded, no. Now, is it compact? Well, it's not closed, so it can't be compact. Now, is it polygonally path connected? Well, we can see, actually, yeah, we can just draw a line between any 2 points. So if we have some point A here, we have some point B here, we can just draw a line here. And we can see that any 2 points are going to be polygonally path connected. So, yep, it is polygonally path connected. It's simply path connected. I mean, simply polygonally connected. Well, we can also see that, yeah, it's no holes, simply polygonally connected. And as a region, it's not open, so it can't be a region. And whatchamacallit, the most interesting part is this S3 here. So let's erase this. So what is our set S3? Our set S3 is just a single point. Is this point, which is 1 plus I. Now, is it open or closed? Because I think I remember there was some kerfuffle in the first lecture where I was like, oh, are lines closed? Are like circles closed? Whatever. Like, apparently the Moodle was pretty bugged, but I'm pretty sure it was just they defined this to be closed in previous previous iterations of the course. But currently we will not define this single point. We won't define lines. We won't define just a circle as closed. We'll define it just as none. So for this point S3, it will be neither open or closed. And since it's not open or closed, it's not going to be compact. It's not going to be a region. So is it bounded? We can just pick a circle that takes it in. Yeah, it's going to be bounded. Is it polygonally path connected? Simply path connected? Well, I believe vacuously yes, but I'll go check. Is it? Oh. Wait, what? Yeah. So yeah, I'm pretty sure it's vacuously true. So yeah, and then like set for. Do we have time for set 4? Do you want to do it or just want to move on? Yeah. Okay, that's fair. So, all right. So we now move on to functions. So what is a complex function? Because a complex function isn't necessarily just a function that maps A to B, where A and B are subsets of the complex plane. It's not necessarily that. It might be that in other places, but in this course, we also require at least one of A and B to not be real, to not be a subset of reals. So, and most of the concepts for real analysis just carry over to complex functions, just because, I don't know, magic, it just works that way. It works really nicely. There's a reason we did think of complex numbers. And one of the most common ones, like you saw this in our class test, it's the fractional linear transformation. So these are just the functions in this form, az plus b on cz plus d, where like the numerator and denominator are linear functions. So one very important thing that quite a few people neglect, is that our fractional linear transformation, if it always maps circles or lines to circles or lines. Except there's like a few cases where it doesn't, but it leaves out exactly one point. But for the most part, it maps circles to lines, circles to lines or circles, lines to circles or lines, and we can observe as z goes to d minus c, what happens to this denominator is this actually approaches 0. And the way it approaches 0 is from all directions as well. So it's not really, we can't necessarily just limit it. It kind of limits to everywhere in a sense. So let's look at an example of how we find the image of certain sets under fractional linear transformations. So we consider this fractional linear transformation here. Tz is w, which is just 1 on z plus I. And we want to find the image of this line, 3x plus y is 1. So we kind of just we could just bash it out, right? So we just let z equals x plus iy, and then we let our w equals u plus iv. From there, we can just do the math. We do this, see this, and then you work it out. So we find x in terms of our u and v, and then from finding our x in terms of u and v, since we know some properties of we know the relationship between x and y, which is 3x plus y is equal to 1, we can find some relationship between the u and v here. So from finding that relationship, we can deduce we can just deduce stuff, and we rearrange it, we eventually get this thing here. So that's one way to do it. You can just kind of bash it out, you can work it out, which it's a way that always works. And I think that's very important. If you're stuck, if you don't really know how do I approach this, you can always just bash it out. However, one other way is that, remember from before, every circle or line always maps to a circle or a line. So if we know we're finding the image of a circle or a line, we just have to find 3 points. If we know where the 3 points are, we know what the circle or line is. Because let's say we consider the image of 3 points is not collinear. That 3 points define a circle, so we know what the circle is. However, if the 3 points we find are collinear, that means the image isn't going to be a circle, it's going to be a line. So that's another way we could find the image of our fractional linear transformation. It's, as we can see here, so we consider another fractional linear transformation where it's just z plus 1 on z plus I, and instead we're trying to find the image of this circle here, x squared plus y plus 1 squared is equal to 1. So what this set C looks like, it's just a circle. What does it look like? It's y is minus 1. It should look like this. Yep. Plonk. So this is minus I. It passes through 0. It passes through minus 2i. But also passes through 1 minus I minus 1 minus I. So here, you can kind of see it'd be pretty efficient if we just found the image of 3 points. So what 3 points we pick? We pick nice points. So we just pick here, we picked 0, we picked 1 minus I, and we picked minus 1 minus I. So where does 0 map to? We just put it in. It's minus I. Where does 1 minus I map to? It's just 2 minus I. And where does minus 1 minus I map to? It maps to I. So what would this look like? So if we just draw this, we get that the points map to this point here, which is minus I. It maps to here, which is I, and it maps to over here, which is 2 minus I. And we can kind of observe that they all lie in the circle center 1 and radius root 2. Since the distance between all of these is going to be root 2. So from there, instead of just trying to just like bash it out. We can just find our 3 points. And we found our 3 points, we found that they're not collinear, and we found this circle here. So we can see that the 3 points just lie in the circle, and thus the image of this circle is C prime, which is just this. Right? We all understand that? Okay, like, where's Rashid, bro? All right. Do I just go through it? Okay. So the person who's supposed to like do this part isn't here yet. So I'll just cover it for now. So if it's not as good, just keep that in mind. Sorry in advance. So okay. So how do we define limits? Well, if we recall to our 1241 lectures, our limit is basically kind of just as we get close to some value, what will it look like? Like, what does the function look like? So the limits here are kind of the same. What happens if we get close to a point? What does the behavior look like? So existence of limits, a limit just doesn't exist if the limit attains different values along the paths. For example, if we just have some z here, so if z1, if along this path towards z1, if we get like, I, if this path gives us minus I, it just doesn't have a limit, right? And it exists if every single path, if we move along every single path, we get the same value. And also just the epsilon delta definition from Math 1A and Math 1B, where instead of this like absolute value thing, meaning absolute value, it means like distance, like how close are you to your z0. So you kind of understand that? Yeah. So let's look at an example. Prove that the limit doesn't exist. So what do? We note that as z approaches 0, we get that r also approaches 0. So we get that the limit here, if the limit exists, the limit here would just be the limit of r to 0 of this. And we can rearrange this to r sine theta, and we can rearrange it, it's sine theta on e to the I theta. And you can just see that this isn't going to be the same for all different theta, for all different paths. So we get that the limit doesn't always exist. Well, the limit just doesn't exist. Does it follow? Okay. And continuity. So similarly to Math 1 and Math 1B, we define continuity the same way as we define it there. Basically, the limit, the point is the limit. The value of the function is the limit. So we get the sums, products, quotients, and composition of every continuous function is always going to be continuous where it is defined. And let's look at an example. So we proved that some function with imaginary, what did we prove before? We proved that the imaginary of z on z is not, what did we prove? The limit doesn't exist. But now here, we're just going to prove that f of z is imaginary element of z is continuous. So how do we do this? We use epsilon delta definition. So we're required to prove that as z approaches z0, f of z is equal to z0. And how we do it, we just, so hence using definition for all epsilon there exists delta. So if we get arbitrarily close, so if we just choose our delta to be equal or epsilon, we get that just from, since the imaginary of z minus z0 is less or equal to z minus z0, because if we look at it from picture, this is the difference Oh wait, no. This is the difference of the imaginary minus z0, whereas this is z minus z0. And Pythag. So you can just see that if we set our delta to equal our epsilon, we get the desired inequality. And thus from there we get the limit exists. So you kind of see the idea? Okay. And yeah, differentiability defined similarly. And similarly to like when we deal with reals, differentiability of a function does imply continuity. And yeah, and the differentiation rules also apply here. So Cauchy-Riemann equations. So, how do you explain this? So when's it coming? Okay. So what is a Cauchy-Riemann equation? So one condition, like for most complex functions, we can use the Cauchy-Riemann equations to determine if a function is actually differentiable or not. So with every complex function, we can split it into real functions u and v. And if we get the partial derivatives, if we get u and v are the partial derivatives with x and y exist for both of them, that means it means that the derivative of the original function exists if and only if these two things hold. And we get the derivative just by differentiating with respect to x for both of these. So yeah. And an example, which of the following functions are differentiable? Well, what I can do, we can apply Cauchy-Riemann equations. So our first function, f1 here, we get it's equal to this, and we get our u is x cubed plus x y squared, and our v is going to be y x squared plus y cubed. Okay, yeah, come, bro.
Next one.
Yeah. That's fine. Yeah, sorry.
I'm gonna have this on the side.
Okay. Wait, just hold on to mic. Wait, yeah, we're transferring over. Yeah, sorry.
Is there a webcam? No? No, okay.
Can I use my laptop again? Thanks.
Okay, well, we switched over presenters. I'm Rashid. I'm going to take over for the rest of the seminar. We're up to the examples of applying the Cauchy-Riemann equations to determine where functions are complex differentiable. So the general method for this is going to be separating the given function into its real and imaginary component, and then plugging those components into the equations. And that'll allow us to determine where the functions are differentiable, because that's going to be where those equations hold. All right, so for this first one, we have that our function is z times the modulus of z squared, right? So if we rewrite that as a function of x plus iy, we have that f of 1 of x plus iy is equal to, well, obviously z times the modulus of z squared, which is equal to x plus iy times x squared plus y squared. That's the modulus squared, right? And then separating that into its real and imaginary components, we get, as the real component, we get x cubed plus xy squared. And then as the imaginary component, we get x squared y plus y cubed, right? So let's see what that looks like when it's substituted into our equations, right? So our first equation, which is that delta u over delta x is equal to delta v over delta y, that's equivalent to saying the derivative of this first part with respect to x, which would be 3x squared plus y squared, is equal to the derivative of the second part with respect to y, which is x squared plus 3y squared. And with some algebraic manipulation, we get that x squared is actually equal to y squared, which implies that x is equal to plus or minus y, right? So this is our first condition. This is the condition that we need for the first equation to be satisfied. For the second equation, we have that delta u over delta y is equal to negative delta v over delta x, right? And that's the same as saying that 2xy is equal to negative 2xy, right? Which is only true when xy is equal to 0, right? So looking at our two conditions, right, x and y equaling 0 and x equaling plus or minus y, we get that 1 and 2 hold if and only if x equals y equals 0, right? So what does that mean? That means that our function is only differentiable at the origin, the point where x equals y equals 0, all right? So this is essentially what we do in our solution as well, that we have written here, right? Substitute into our equations, and we get that x equals y equals 0 is the only place where the equations actually hold. All right, what about this second question? Our function is x cubed plus I y cubed, right? Luckily for us, it's already separated into its real and imaginary components. So let's just rewrite that here. Is equal to x cubed plus I y cubed. So u is equal to x cubed and v is equal to y cubed, right? That means that in order for our first equation to hold, which is delta u over delta x equaling delta v over delta y, we need that 3x squared is equal to 3y squared, right? And again, we get that x squared equals y squared, so x is equal to plus or minus y. That's our first condition. Second condition, that's delta u over delta y being equal to negative delta v over delta x, right? And that's equivalent to the derivative of u with respect to y is the same as the derivative of a constant with respect to y, because there are no terms that are dependent on y. So it's going to be 0 equaling negative 0, which is obviously always true, right? So 1 and 2 hold if and only if x equals plus or minus y, right? And that'll be on the complex plane, that'll be all the points along these diagonals, right? So along these diagonals, our function f2 will be complex differentiable. And our last function is absolute value of x plus I absolute value of y. So f3 of x plus iy is equal to absolute value of x plus I absolute value of y. Nope. Okay, so here again, u is equal to absolute value of x, v is equal to absolute value of y. Our first equation would be delta u over delta x equaling delta v over delta y, which is equivalent to, what's the derivative of the absolute value of x? It's the sine of x, so whether it's positive or negative, which you can express like this. And v, and the derivative of the absolute value of y with respect to y will be same thing, y over absolute value of y, right? And let's just write out the second one real quick. The second one will again actually turn out to be equivalent to 0 equaling 0, right? Because our function u has no terms dependent on y. So delta u over delta y is equal to negative delta v over delta x, which is equivalent to 0 equaling negative 0. Okay? So the condition that we obtained from this one, if we have a look, so here we have our first condition, which is that x over absolute value of x is equal to y over the absolute value of y. This implies that x over y is equal to the absolute value of x over y, right? We just move over the x and the y to the other sides. And this will be true when x over y is larger than 0, right? So when x over y is a positive number. So our function is differentiable at all the points where x over y is larger than 0. Alright, moving on. Holomorphic functions. Holomorphic functions are actually pretty central to this course. And the definition is a bit subtle. So a function is said to be holomorphic at a point z, right? I'll draw that a bit bigger. So a function is said to be holomorphic at a point z if the function is differentiable within some neighborhood around z. No matter how small that neighborhood is, right? As long as it's differentiable in some region surrounding z, right? This turns out to be quite a restrictive property. It implies that the function is actually infinitely differentiable at that point z, right? And it also means that it's locally equal to its own Taylor series around that point, right? And a function that is holomorphic across the entire complex plane is called entire, right? Now, one thing to note is that a function can only ever be holomorphic on an open set. So if the function is differentiable on a closed set, it will not be holomorphic on that whole set, right? And this comes from this definition of a function only being holomorphic at a point if it's differentiable in a region around that point, right? So if you imagine a function f being differentiable on a closed set like this, it won't be holomorphic on any of the boundary points, right? Because it's not going to be differentiable in a neighborhood around that point, right? So it'll only be holomorphic on all the interior points of that set, but not on the boundary points. Another thing we need to know is that harmonic functions, right? So if we have a function of two variables, right, say u, we say that it's harmonic if and only if it satisfies this equation. So the second derivative of u with respect to x plus the second derivative of u with respect to y is equal to 0. along with the fact that all first and second partial derivatives exist of that function and are continuous across this domain. Another thing that you need to know is what's called the harmonic conjugate, right? So if we're given some holomorphic function f, right? But we're not given the whole function, but just either its real or its imaginary component, then we can actually use the Cauchy-Riemann equations to derive the other component, the one that we're missing, up to a constant, right? And that other component that we're solving for is called the harmonic conjugate, right? So U is the harmonic conjugate of V, and V is the harmonic conjugate of U, if F is a holomorphic function. So let's move on to an example, right? This question asks us to show that this function U asks us to show that the function U equaling sine x sine y is harmonic, and to find a harmonic conjugate, right? So showing that it's harmonic is pretty straightforward, right? So you find the second derivative of U with respect to x, and you find the second derivative of U with respect to y. Add these two together, right? And you get 0, which means that U is harmonic, right? Finding a harmonic conjugate is a little more subtle. So first we have to find an expression for V, right? So we have that f, our function f that we're looking for, is equal to U plus IV, right? And we have U, we're trying to find this component V. They're related through the Cauchy-Riemann equations because we know that f is holomorphic. So we know that delta V over delta y is equal to delta U over delta x, right? And delta U over delta x is just the derivative of the expression we're given with respect to x, right? Which is cosine x sine y. Oh. And now we have an expression of the derivative of v. So if we integrate it with respect to y, we'll get an expression that looks something like what v should be, right? So when we integrate it, we end up with v equaling cosine x cos y plus some constant of integration. But because we're integrating a partial derivative, right, this constant of integration actually has to be a function of x, right? Because if you imagine taking the derivative of this whole expression with respect to y, no matter what this function of x is, it's still going to just become 0 after you differentiate it, right? So we have no idea what this could be. It doesn't have to be a constant, it could be a function of x, right? So we have to leave that there and then find out what it could be. So our next step is to find out what this function c of x has to be. So what we do is we use the other Cauchy-Riemann equation, right? The one where we have that delta v over delta x is equal to negative delta u over delta y, right? Which is equal to, from our expression of u, that should be equal to minus sine x, minus sine x cos y minus sine x cos y. Now we have, if we differentiate our expression for v, right, we'll get that this also has to equal minus, we'll get that it also has to equal minus sine x cos y plus the derivative of our function c with respect to x, right? And comparing these two expressions, right, we realize that the derivative of c with respect to x has to be 0. So c of x has to be a constant, right? So c of x is some constant c. So if we can choose any constant to be c, so we can choose it to be 0, and we found that a suitable harmonic conjugate is cosine x plus times cos y. Cosine x times cos y. All right, moving on. The exponential function, right? We define a particular function as an infinite series, right? Where each term is z to the n over n factorial, from n equaling 0 up to infinity, right? This series should look pretty familiar. And the reason it looks familiar is because it's the Taylor series for e to the z, right? And since e to the z is holomorphic everywhere, that means that e to the z is actually going to be equal to this series everywhere, right? And that means that this function that we've defined is just another way of writing e to the z. And of course, it's going to satisfy all the same identities as the function, as the exponential function, e to the z. So, you know, when you're adding two things in the exponent, that turns into multiplication. And it's also periodic with 2 pi I, just like e to the z. We can use the exponential function to define the hyperbolic functions, right? Cosh and sine. They are the even and odd components of e to the z, respectively, right? And they also take on, they're also made with the all the even and odd terms of the Taylor series of e to the z, respectively, right? So these ones you can see it just takes on every even term of that Taylor series. This one just takes on every odd term. These two functions have some pretty neat properties, right? We've got an Nagle-sum identity, which is worth remembering for both of them. And they also are their own derivatives, right? So derivative of cosh with respect to z is sine z, and the same thing for sine. Some other properties, as I've said, cosh is an even function, sine is an odd function, and they're both periodic with 2 pi I, right? Because e to the z is periodic with 2 pi I, that means that any function made of, you know, copies of e to the z is also going to be periodic with that, with the same number. And it has this, we have this identity as well, that cosh squared minus sine squared is equal to 1, right? Kind of similar to the Pythagorean identity for trigonometric functions. And speaking of trigonometric functions, we can also use the exponential function to define them, right? Here, we're using the fact that the real component of e to the I z is cosine of z, right? And the imaginary component of e to the I z is sine of z, right? And that means that if you add e to the I z to its own conjugate, and then divide by 2, you'll just get out its real component, cosine z, right? And with sine z, if you subtract the conjugate of e to the iz from e to the iz and then divide by 2I, you're going to get its imaginary component, which is sine of z, right? Here are the Taylor series for the two functions. They're the same as the Taylor series on the real line, which we've learnt in 1231 or 1241. They also have some interesting properties that relate them to the hyperbolic trigonometric functions, right? Namely that sine of iz is equal to I sine of z, and cosine of iz is just equal to cosh of z, right? And these are worth remembering, but even if you forget them, they're pretty easy to rederive. You just have to look at what happens when you plug in an imaginary number into our definition of the hyperbolic functions, right? You see that if you plug in cosh of iz, you just get something that looks identical to our definition for the cosine function, for instance. All right, moving further on, right? Now that we've defined an exponential function, the natural question to ask is there the equivalent of a logarithm in the complex plane, right? The issue with having a logarithm for the complex exponential function is that ideally the logarithm should be the inverse of the exponential function, right? Because that's how it works on the real line. But the problem is that e to the z is not a bijective function. It's not one-to-one, right? For instance, e to the z is going to be equal to the e to the z plus 2 pi I, right? It's periodic with 2 pi I. So it's not clear what particular value for z the log function should output for a given input, right? Because it could be a particular logarithm, but it could be that same logarithm but plus 2 pi I, right? And they would both work as solutions to e to the z equaling w. So in fact, right, if you took some equation, right, that you wanted to solve, like e to the z equaling 1, there's actually an infinite family of solutions for z that would work, that would satisfy this equation, right? For instance, 0 would work, plus or minus 2 pi I would work, right? Plus or minus 4 pi I, right? An infinite family of solutions, and they all differ by multiples of 2 pi I, right? So if we want to actually turn our complex log into a proper function, we're going to have to isolate a particular branch of it, right? Which means you just have to specify which of the solutions is going to output out of this infinite family of possible solutions, right? So the branch that we're going to be using most often in this course is called the principal branch, right? It's defined like this. It uses the principal argument, hence the name. And because it uses this arg function, there's no longer any ambiguity as to what the imaginary component has to be, right? It's pretty easy to verify here that that e to the log z is going to equal z, right? No matter what z is. The issue with this definition, though, is that because of this arg function, we actually introduce a discontinuity, right, into our function. Our log function is going to be discontinuous, right? I'll show you what I mean. If this is our complex plane, if this is our input plane, right, and we'll have our definition for log z up here. The natural log of modulus of z is going to be continuous everywhere except 0, right? That's pretty clear. But arg is where we start having issues, right? Because it's actually going to be discontinuous along this entire ray, right? the entire negative real axis. And that's because that negative real axis is when that arg function jumps from a negative value to a positive value, right? A point here is going to have an argument very close to pi, right? But a point here is going to have an argument very close to negative pi, right? So if a point crosses over this boundary, it's going to have to jump from an argument of negative pi to pi. That's basically what the discontinuity, where the discontinuity comes from, right? So that's something to be aware of when you're working with this function, right? But other than that, it's pretty well behaved. It takes in almost any input besides 0, right? Because then this natural log of modulus of z would not be defined. And it's differentiable everywhere except along that ray where it's discontinuous, which is called the branch cut, right? I'll write that here. Now, if we want to be more general with the solutions that we output from our logarithm function, we can use something that's called the multi-valued log, right? This is the function that takes as input. So our multi-valued log, multi-valued log function, right? Is going to take as input a complex number, and return the set of numbers that satisfy. So if we have that satisfy the exponential equation that you're trying to solve, right? So if we have that e to the z is equal to w, right? Then actually a better example perhaps would be the one we used before, 1, right? If you're trying to solve this, then then you would take the log of 1, right, to solve for z, and what you would get back is the set of all solutions, right? So 0, plus or minus 2 pi I, plus or minus 4 pi I, etc., right? And necessarily, of course, z is going to have to be part of that set, right? So in a way, we're not losing information anymore when we solve for a particular value of z, because the output of our function contains every possible solution that would satisfy e to the z equaling 1, right? Of course, it also means that it's not a proper function because it doesn't map from C to C, right? It's not a proper complex function. We can write the multi-valued log in simple terms using the multi-valued arg function. Right? And of course the set that is going to output is going to be the infinite family of solutions, all separated by multiples of 2 pi I, which is what we have here, right? 2k pi I, where k is an integer. All right, so let's apply this. We have to solve this equation, cosh of z equaling -2. We rewrite this in using the definition that we learned before, right? And with some algebraic manipulation, we can get it in the form of a quadratic equation of e to the z, right? And we can just plug that into the quadratic formula, which does work for complex numbers as well. And we get that e to the z has to equal -2 plus or minus √3, right? So to find all the possible values of z, we take the multi-valued log, right? Which we write with a lowercase l. That's how we notate a multi-valued log. Multi-valued. Take the multi-valued log of this right-hand side, and we're going to get as output the natural log of the modulus of minus 2 plus or minus root 3, right? Plus I times the argument of that number, right? Now notice that minus 2 plus or minus root 3 is actually going to be negative, right? So when you take the absolute value, you have to flip the sign, right? So the 2 becomes the minus 2 becomes a 2, and the plus or minus becomes a minus plus root 3. The argument of this number, it's a negative real number, so the argument is going to be I pi, and because this is the multi-valued arg, we have to add on the multiples of 2 pi I, right? So what we're saying is that z is of this form, right, where k is an integer. And that solves the equation. Now we have a special notation for the other branches of logarithms, right? We use a subscript of an angle, theta, right? And it's defined as natural log of the modulus of z plus I times the theta branch of the argument, right? And the way this is defined is that the theta branch of the argument of z is going to have to be strictly between theta and theta plus 2 pi, right? And the branch cut is going to occur either when z equals 0, obviously, because it's that would make this term undefined, or along that ray where arg is discontinuous, right? So that's when it's maximized, equaling theta plus 2 pi. So if this is a bit confusing, that's okay. It's actually not too bad, right? The tricky part comes from imagining what that branch of the argument looks like, right? So if you had some complex number z, right, how would you ordinarily find its argument? Well, one way to think about it is that you start here, right? You start in a direction that's pointing this way, right? With the number minus pi in your head, and you keep on rotating anti-clockwise, right? Increasing the angle until you reach z, right? So keep on rotating. At this point, you get some slightly larger angle. At this point, some slightly larger one. At this point, you have an angle of 0, and you keep rotating until you're looking at z, right? And whatever angle you had to rotate to reach that point is the argument of z, right? But what's totally arbitrary is where you start counting that angle, right? So you could start here, right, with the angle 0 in your head, right? In this case, the argument of z will be the same, but the argument of a number that's over here, right, would actually not be negative anymore, because you rotate, right, and reach it only after you've traversed an angle that's larger than pi, right? So if you're trying to find the argument of branch theta of a number z, right, this is the way to do it. First, you start looking forward, right? You start looking in the positive real direction. Say our number z is like here, right? You start looking in the positive real direction, and then you rotate some angle theta, which could potentially be more than 2 pi, right? So this is our angle theta. And then keep rotating until you reach, until you're looking in the direction of z, right? And the angle that you had to rotate to reach z plus theta is going to be the argument of z of branch theta. Okay, maybe that's more confusing than just this simple definition here, but that's the way that I like to imagine it. Just like with the regular log, it's differentiable everywhere except on the branch cut, right? With derivative being 1 over z. The good thing, though, about these branches of logarithms is that the branch cut, the place where it's discontinuous and not differentiable, is in a different place, right? So here's our definition of log theta, a log of branch theta of z, right? It's natural log of the modulus of z plus I arg theta z. So the place where it's discontinuous is where this arg term is maximized, right? Where it jumps from its smallest value to its largest value. And that's going to occur at an angle of theta, right? So if theta in this case is like 3 pi on 4, right? Then this term, arg theta z, right, is going to be strictly between theta and theta plus 2 pi, right? So at this particular angle, right, along this ray at angle theta from the horizontal axis is where it's going to be discontinuous, because a point here, right, is going to be very close. The argument of a point here is going to be very close to, theta plus 2 pi, but the argument of a point here is going to be very close to just theta, right? So if a point crosses this branch cut, then it's going to have to switch from this very large number to this very small number, and that's why it's discontinuous there, right? So basically what this is saying is using a different branch of the logarithm allows us to move the branch cut, allows us to change where it's not differentiable, while still keeping the same properties. So here we're asked to play around with this a little. We're asked to define a branch of log theta, a branch of log of the multi-valued function log z that is continuous at z being minus 1 and has value 7 pi there, right? So obviously this can't be the regular branch of log because it's discontinuous at z being minus 1, right? So let's just write this out. We're asked to evaluate at minus 1, right, which would be equal to natural log of the absolute value of minus 1 plus I arg theta of minus 1. So natural log of 1 is obviously going to equal 0, right, plus I arg theta of minus 1. So we're just solving for this angle theta then, right? There are actually quite a lot of branches of arg that would allow the log to be continuous at z equals minus 1, but we do have this restriction that is equal to 7 pi I. Right? So it means that what we did is that we first rotated the angle theta some amount of turns, right? And then we rotated to meet that point minus 1, and our total angle was 7 pi I, right? So the way that we solve this is that we just recognize that if we took 4 whole turns, if we did 4 whole turns, right, and then another half turn, right, that would bring us facing this axis, right? So if our angle theta was, 4 full rotations, which is 2 pi I, then it would bring us then, sorry, it shouldn't be 4, it should be 3. 3 times 2 pi I. Then this value of theta would actually work, right? Because in that case, we have that theta is less than arg theta z is less than theta plus 2 pi, right? No, sorry, not I. There we go. Because this would be 6 pi, this would be 7 pi, and this would be 8 pi, right? So that's satisfied. And the value of 7 pi I would actually be a valid argument for minus 1, right? Because minus 1 is equal to e to the 7 pi I, right? So we conclude that our branch of logarithm, the branch of the logarithm that we need is log 6 pi z. Okay, now experimenting with the differentiability of the logarithm, right? We know that it's differentiable everywhere except on the branch cut, right? Which is the ray that starts at the origin. So for the principal log, it's not differentiable along this negative real axis, right? Not differentiable along this line. And we're asked to determine where this function, right, principal log of 3iz minus 4 is differentiable, right? So just basically asked to find the values of z where 3iz minus 4 doesn't land along this ray, right, where it's not differentiable. So this is basically what we have, right? We know that 3iz is f is not differentiable when 3iz is along that negative real axis, right? So it's some value, some real number lambda, where lambda is along that line. And when we actually solve for this, we get that if z is on the imaginary axis, right, between minus 4 on 3 all the way up to infinity, that's when f would be not differentiable. So f is differentiable everywhere except for the segment of the imaginary axis from minus 4 over 3i upwards. Yeah.
Conditioning similar to the pad. Can I come down?
Yeah, sure. Do you mind if I keep talking?
No, keep going.
Okay.
Just start with conditioning yourself.
All right. For this next question, we're asked to find all complex numbers z such that sine of z is equal to 2, right? And we're going to be using the same definition as we had before, right? Sorry, we're going to be using the exponential definition that we looked at before. So we have that e to the iz minus e to the minus iz over 2i is equal to 2, right? And we can write this out as a quadratic equation with e to the iz as our variable. And we get that e to the iz has to equal 2i plus or minus root 3i, right? So to find all the valued values of iz, we have to take the log of this right-hand side, right? The multi-valued log. And when we plug that in, we get this value. It's a bit difficult to simplify.
Yeah.
Oh, it's okay?
Yep, keep going.
Yep. It's a bit difficult to simplify, right? But this is the full solution. of course, we can write it out further, dividing the right-hand side by I, right, to get an expression for Z. So, when we actually evaluate this, we get that Z is part of this, is an element of this form, right? So, part of this infinite family of solutions. Because, again, as I've said, right, e to the iz is not a one-to-one function. So we can't determine the value of z that satisfies this uniquely. All right. Another thing that we can do in the real numbers, but we can't do in, that we don't know how to do in the complex plane, is raise numbers to a number power, right? So, you know, in the real numbers, we know how to do like root 3 to the power of pi. We know that this is going to evaluate to a real number, and that real number is going to be unique. We could try defining something along those lines for complex numbers as well. But again, we arise with this issue where z, right, z to the w is not actually always going to be a bijective function. So we have to define a particular branch of this function z, a particular branch of the function z to the a, right? This is, or what we call the principal value of this exponent, right? So how we define this is the exponential function of a times log z. And you can see how this is kind of a natural definition, because in the real numbers, right, if you have, for instance, we'll use the same example, like root 3 to the pi, that's going to equal e times the natural log of root 3, right, times pi, right, because this is just going to simplify to root 3 times pi. There are other branches of this value, right, which we would find by using different branches of this log, right? Or we could use the multi-valued function za, which is defined using the multi-valued log, right? And they're all going to be separated. The exponents that we're going to have in there are going to be separated by multiples of 2 pi I alpha. So defining how to raise numbers to some power also allows us to define how to take the nth root of a number, right? Because that's the same as just raising a number to 1 over n, okay? And the way we define it is exactly the way we have here, right? Just with some simplification. So modulus of z to the power of 1 over n. This is going to be a real number raised to a real exponent, so this is unambiguously defined, times e raised to the I arg z over n, right? And obviously, if you want a different branch of this value, then you use a different branch of the arg here, right? This could be arg theta. Otto, how are we going for time? Alright. Okay. So, here, we're just going to apply this and try to find the multi-valued, the set of values that could correspond to I to the 2 minus I, and also the principal value of I to the 2 minus I, right? So basically what we do is we just plug these values into our expression, right? We know that z to the w is equal to e raised to the w times log z, right, where log is the multi-valued log. So when we plug that in, and we recall that the multivariate log is separated by multiples of 2 pi I, right? And we simplify, we get this, right? So minus e to the power of pi over 2 plus 2k pi. The principal value of that is just going to be the same thing, but without this multiple of 2 pi added on. So just minus e pi over 2. Minus e to the power of pi over 2. Alright, maybe I'll speed up a little. This is a long question. Onto curves, right? So, a curve, the way we define curves in this course is just basically a formalization of kind of an intuitive notion, right? A curve is something that's traced out from one point to the other, right? So in this course we define it as a continuous function, right, that maps from the real numbers to the complex plane, right? Specifically the real numbers along a given interval, right? So the initial point of the curve is what we call gamma of A, if A is the initial point of our input space, and the final point is the function evaluated at the final point of our input space. The range of a curve is just the set of points attained by that curve between those two inputs, right? So this entire set of points. And a curve is closed if intuitively it just forms a loop, right? And what that would mean in terms of our definition is that the function value at the start of the interval is equal to the function value at the end of the interval, right? We also call the curve simple if it doesn't cross itself, right? So this one is simple and closed. But a closed curve that looks like this would not be simple because it crosses itself here. So that should be pretty intuitive. We can classify these curves as simple or closed. This one is clearly not closed, but it is simple. This one is closed, but it's not simple. And this one is closed and simple, right? Should be pretty simple. All right, moving on. We have this operation that we can do on curves called a join, right? And this is also pretty intuitive. If you have two curves, right, where the second one starts where the first one ends, right? Say this one is called A and this one is called B, then this entire curve, right, is called the join of A and B. So we use this symbol that looks like a square cup, which represents the disjoint union, right, of A and B. We also have something called the reverse curve, right, represented with a star. That's just a way to notate the same curve but traced backwards, right? So instead of the function going from the start point and going to the end point, the reverse curve would be a function that starts from the end point and goes to the start point. Okay. This should be pretty familiar, by the way, because this definition of curves is just what we called a parameterization in high school, right? A parameterization of a curve. So we can parameterize lots of things, like lines and circles, right? We usually parameterize lines as a weighted sum of the 2 points, right? So this is how we would write it out. You can see that when t is 0, then this part would be 0, and this part would just be z0, right? It doesn't change. And when t is 1, then this would become z1 minus z0 and cancel with this part, right? Leaving just z1. So it's a parameterization of the line segment between z0 and z1. For a parameterization of of circles, we use the exponential function, right? Because as t goes from 0 to 2 pi, that's going to trace out this circle of radius r. We can take derivatives of curves, right? Because a curve is just a function of a real variable, we don't have to worry about Cauchy-Riemann equations or anything like that. We just take the derivative with respect to t, and we can do that by taking derivative of the respective components, right? We have concepts that we apply to curves, such as continuous differentiability, right? It's continuously differentiable if the derivative exists and is continuous on the input space, right? This segment from A to B. We say that it's smooth if it's continuously differentiable, and that the derivative never equals 0 for any point in the input space, right? And we say that it's piecewise smooth if it is a join of a bunch of different curves, right? And all of those curves separately are smooth, right? So this would be if this particular curve is smooth, right? This particular curve is smooth, and this one is smooth, right? Then this entire curve would be piecewise smooth. It's not actually smooth because it has these, sharp points here, but it is piecewise smooth because the pieces are smooth. Yeah. So here's an example of a join, right? This join is piecewise smooth because each of the points are smooth, right? So here we have to verify whether this function t cubed plus I t cubed is smooth. So basically the one thing that we have to check for is that the derivative exists across the input space and that the derivative is never 0, right? The derivative does exist. It's equal to 3t squared plus 3it squared. But unfortunately, if you plug in 0, then the derivative would be 0, right? So this curve is not smooth. And some intuition for the smoothness of a curve. To be smooth, the curve must have no sharp corners or cusps, but the parameterized point must also never stop. That would correspond to the derivative being equal to 0. Okay, something that should ring a bell from when you did 1231 or 1241 is the length of a curve, right? It's the integral from A to B of the modulus of the derivative of the curve, right? Because you're adding up the lengths of the line segments traced out by the parameterized point, right? That would give you the length of the curve. So here we're finding the length of this curve, right? Which should be pretty obviously just the parameterization of a circle, right? Traced around n times. So if we actually do take this integral, we get the integral of r from 0 to 2n pi, which is 2n pi r, right? Which should make sense because this curve is defined to just be a circle of radius r traced around n times. Now a contour is the oriented range of a piecewise smooth curve gamma, right? So whereas gamma were functions, a contour is just a set of points. It's just a set of points that's described by a curve together with the direction in which it has to be traversed, right? So sometimes you'll be given a contour, right? That looks like this, for instance. Actually, no, there's a bad one. So say on the complex plane, you'll be given a contour, right? That looks maybe something like this. And the way that the direction will be specified is that you'll be told whether it's traversed anti-clockwise or clockwise, right? And that's enough to actually specify which direction you have to go. And if no direction is mentioned, then you just assume anti-clockwise traversal. So we go on to complex integration, right? So we're defining the integral of a complex valued function that has as input a real value and as output a complex value, right, with real component u and imaginary component v. Luckily, when we take these sorts of integrals, we can just integrate the components separately, right? And that turns this complex integral into just two real integrals, right? Very easy. Yeah, effectively, we're just treating the imaginary unit I as just another constant, right? So, just as with real integrals, we have basically the same identities, right? Adding together two integrals or multiplying them by some constant is going to yield the same results. So you can separate them out and bring the constant out of the integral. You can use substitutions, right? Here the substitution was t equaling h of t. And yeah, we also get this what we call the ML property, right, which gives us a bound on how large the absolute value of an integral can be, right, which is the same as for real numbers. Okay, so let's have an example, right? So here we're actually given a purely real integral to evaluate, but we can use complex techniques to evaluate it, right? We can notice that cosine of t is just the real value of e to the it. So our integral becomes the real value of e to the t times e to the it, and we can rewrite that as the real value of this complex integral, right? We can swap the order of this real function and the integration. Evaluating this integral is pretty easy, right? Because we can just bring this e to the t into the exponent, right? And then we're just integrating an exponential function with a linear exponent, right? Which is quite easy. We get this value, and we're taking the real part of this value to find our answer, which turns out to be e to the 2 pi minus 1 over 2. Okay, now onto something a little bit harder. We're taking integrals of complex functions that have a complex input rather than a real one, right? Because we're now integrating in a plane and not in a line, along the real line, that means that our path of integration, right, can actually be whatever we choose, basically, right? It can be any contour or curve that we choose. So, how do we evaluate this? Well, we can turn it into a sort of semi-real integral that we evaluated before, right? The way we do that is we substitute in our parameterization of the curve, right, gamma t, multiply it by the derivative of our parameterization and dt, right? So basically we're just using the substitution z equaling to gamma of t, which is a perfectly valid substitution because at every step along our integral, z is going to be equal to gamma t for some value t, right? Because we're only evaluating along this curve. So the reason this is good is because this allows us to turn a complex integral, which can seem quite opaque, into a real integral, which we know how to do. Some of the same properties apply here, right? If we're adding together two integrals, we can separate the integrals and also pull out constants to the front. If we integrate along the same path, right, but in the opposite direction, so if we integrate along this path, we're going to get an answer that's equal to the negative of what we get traversing in this direction, right? Which kind of makes sense. It's equivalent to when you flip the bounds in real integration, right? Except in this case, you're reversing the entire curve. And here, if gamma is the join of two curves A and B, alpha and beta, then you can take the sum of the integral along those curves. Okay, so here's an example, right? We're given a complex integral, right? And we're given the curve along which we integrate, right? Gamma here is the unit circle. So it doesn't specify which direction we actually traverse gamma in, but in this case it doesn't actually matter, right? As you'll see. And the unit circle means we're traversing it once, right? So a parameterization that we could choose for this curve is gamma of t equaling to e to the it, where t goes from 0 to 2 pi, right? So you would start here and it would traverse around and complete one full rotation. And when we substitute that in, we get an integral like this, which is just an exponential with a linear term. And that's very easy to integrate. When we evaluate that, we actually get 0. So in this case, it didn't matter which way we traverse the integral, which way we traverse the unit circle, because the answer will be 0 anyways. All right, a little bit of a trickier one, right? Here we're integrating the conjugate of z, which is a function that obviously doesn't exist along the real line, or isn't defined along the real line. So here we substitute in our parameterization that we've already been given, t plus it squared. And when that's substituted into our function f, that means that we take the conjugate of t plus it squared, which turns out to be t minus it squared, and we're multiplying by this term, the derivative here, and dt. So it turns out that we're just integrating a polynomial of t, which we know how to do from real calculus, and it evaluates to 1 plus I over 3. Okay, a concept we can introduce is reparameterization. So this kind of formalizes the idea that if you have a given curve, it doesn't matter which parameterization of the curve you choose, because if you integrate along it, then the value will be the same, right? So here, how we define a reparameterization is using a bijection, continuous bijection from one interval to another, right? So here h is a bijection from the interval c to d onto a to b, and we define h of c equaling a and h of d equaling b, and we call the composition of those two functions, right, the bijection and our curve, a reparameterization of gamma, right? And the important fact is that using a reparameterization of gamma to integrate something will actually yield the same result as integrating just along gamma, right? Okay, this is something a little bit different. This is us using a property of the complex integral to estimate the size of the value that we're going to get, right? So if you remember from before, one of the results that we had, one of the properties, is that the modulus of the integral of f of z dz is going to be smaller than or equal to the integral across gamma of the modulus of f of z dz. And if we have some value m, right, a maximizer, for which f of z is strictly smaller or equal to m across our curve gamma, then we know that this is going to be, this value here is going to be smaller than integral of m across gamma, right, dz. And that's going to be equal to m times L, which is the length of the curve gamma, right? And this is what we have here. So the absolute value of our integral is going to be smaller than or equal to ml, where m is the maximum, a value that's small, that's greater than or equal to the maximum of the modulus of f of z across our curve, and L is just the length of the curve. So let's apply this to this function here, right? So we have to find, we're asked to find the absolute value, the modulus of this integral as r goes to infinity, right? Where r is the radius of the circle across which we integrate, right? So yeah, gamma denotes a semicircle, right, traversed anti-clockwise, of radius r. So we can see, applying the circle inequality here, that z to the 4 plus 1, modulus of z to the 4 plus 1 is going to be greater than or equal to z to the 4 minus 1, which is equal to the r to the 4 minus 1, right? So we have that our maximizer, right, m, we can set as 1 over r to the 4 minus 1, right? Because it's going to be strictly larger than or equal to the modulus of 1 over z to the 4 plus 1. And since our curve, gamma, is just a semicircle, right, the arc length of it is going to be pi r, right? So by the ML lemma, we know that this value is, the modulus of our integral, is always going to be smaller than or equal to pi r over r to the 4 minus 1. And as r goes to infinity, this right-hand side is going to go to 0, right? Which means this left-hand side, because it's wedged between that and 0, is also going to have to go to 0. All right. Now onto contour integration, right? So this is a little bit different because we're integrating across, again, a path in the complex plane, right? But this time we're integrating across a contour, right? So we're not actually given a parameterization of this curve or this path, but rather we're just given the set of points across which we're integrating along with the direction we have to traverse, right? And that's what a contour is. So we have a theorem concerning contour integrals where if omega is a simply connected domain, so, and f is holomorphic on omega, right? And that gamma, capital Gamma, is a closed contour in omega, then the integral across gamma of f of z dz is going to equal to 0, right? So that might seem a bit confusing, but essentially what this is saying is if you have a closed contour, right, so a loop, right, and our function f is holomorphic everywhere along and inside the loop, right, then the integral along that contour is going to equal 0, right? Always. Which is pretty cool, right? Because it has some interesting consequences. So here's a restatement of the theorem. Suppose that omega is a bounded domain whose boundary consists of finitely many contours, gamma 1, gamma 2, gamma 3, on and on to gamma n. And suppose f is holomorphic on an open set containing the closure of omega, right? Which is omega together with all its boundary points. Then the integral of f of z along the boundary of omega, that's what this represents, right? The boundary of omega is equal to the sum of the integrals across all those contours, right, which join to make our boundary, and it's going to equal to 0, right, because again we're just integrating across a loop along which and inside of which f is holomorphic, right? And this turns out to be quite a powerful result because it can help us evaluate some pretty difficult integrals. So this function, right, we're asked to integrate it along this contour, which denotes the unit circle, right? Now that we know this theorem, the first thing we should check is whether it's holomorphic along and inside that contour. And it turns out that it is, because the only place where it's not holomorphic is when z is equal to minus 1 plus I, which is when this denominator would equal to 0. So that means that it is holomorphic along and inside our contour. And that means that our integral will evaluate to 0. And that's what we have here. Right? Very easy. There's some consequences of this theorem. One is the independence of contour, right? So if we have two contours that start and end at the same spot and are traversed in the same direction, right, then the integral along this one and along this one is going to be equal the same, right? Assuming they're both in omega, the space along which f is holomorphic, right? And the reason for this is it should be pretty clear. It's because these two curves together actually make a loop, right? So the integral along this one, the integral along gamma, minus the integral along triangle, right, is going to equal to 0, right? And that means that integral along this contour is equal to integral along the gamma contour, right? Also, another consequence is the existence of primitives, right? Which should be reminiscent of real integration, right? So if omega is a simply connected domain in C, and f is holomorphic on omega, then there exists a function capital F, right, the antiderivative of f, on omega, such that the integral across gamma of f of z depends only on the start point and end point of gamma, and is equal to f of the end point minus f of the start point, right? So yeah, this is basically equivalent to the fundamental theorem of calculus that we learned in high school, right? Except now it's complex. We just have these extra conditions that f has to be holomorphic on this set where all those contours exist. Yeah, and we call capital F the primitive or antiderivative of f, just like with real integration. So, how are we going for time? I'll go through this question and then we'll probably have to wrap up. Yep. No? All right. Okay. So here, we're asked to integrate this function, z minus 1 to the power of minus 1, so 1 over z minus 1, along a contour gamma. Along a contour gamma, which is specified to be between, which is specified to start at I and end at minus I, right? So from here to here, and lies entirely in the set where the real value, the real component of z is smaller than or equal to 0, which means it's in the left half of the plane. So it's a contour that looks something like this, right? So here is a problem that we have, right? In this case, we cannot actually apply Cauchy-Goursat as easily as before because we're integrating along a path because our function z minus 1 to the power of minus 1 isn't actually holomorphic everywhere, right? It's not holomorphic at the point z equals 1. And that means that a contour that traverses in this direction, for instance, right, the integral along that one, could have a different value to the integral that traverses in this direction, right, the direction that we want. So it is not necessarily true that whatever antiderivative we find is going to be the correct one. So how do we fix this? Well, we apply this fact that turns out to be pretty useful, which is that the integral of f of z dz along the curve gamma is equal to f of q minus f of p, right? Where where p is the start point and q is the end point of gamma. If f is analytic, or otherwise holomorphic, on our path of integration gamma, right? So before we actually evaluate what our integral should be, we have to verify that this is true, otherwise we'll get the wrong value. So the most obvious antiderivative that we can find is log z minus 1, right? That's the derivative of that will be 1 over z minus 1. But it's not a valid choice because this function log z minus 1, as you know, will be is not analytic or holomorphic along this ray, right? That extends to the left of 1. But our contour gamma has to pass through that ray, right? So we can't use it. That means we have to use a different antiderivative, right? Namely, a different branch of log. So we just need to choose a branch of log which has a branch cut that doesn't intersect with our path, right? Preferably one extending in this direction. So we can choose a branch of log whose branch cut is lying along the positive real axis, right? And that would completely avoid our path of integration. We could choose our antiderivative to be log 0 of z minus 1, right? And that means that the branch cut of our antiderivative will actually happen, will actually be along the ray where arg of z minus 1 is equal to 0, right? Which is this ray that extends to the right and doesn't intersect our path of integration. So if we use this as our antiderivative, we'll actually get the right answer. So let's see what it evaluates to, right? Yeah, a valid choice of our primitive f of z is log 0 z minus 1. And when you evaluate that, we just plug in our endpoint and start point, right? Find the complex logarithm of those values, and it evaluates to pi I over 2. That's our answer. All right. And we're on to the final question of this section of the seminar, which is actually a tricky one because we have to apply a lot of what we've learned so far, right? We're asked to evaluate this integral, right? A real integral. But this integral is actually very tricky to determine with real techniques. So we're going to have to apply complex techniques, complex integration techniques to identify the value, right? And the question tells us to integrate this function f of z equaling e to the iz over z along a contour. So before we actually jump into the solution, let's find some intuition as to how we could approach this, right? So we're given this function f of z being e to the iz over z, right? And the integral we want to find is sine x over x, right? Which, we can rewrite as sine z over z. Doesn't matter what variable we use, it's still the same integral, right? And preferably we should rewrite this somehow in terms of this function, right? So we know the definition for sine z. That means we can rewrite this integral as e to the iz minus e to the minus iz over z dz, right? And if we separate that out, we get 1 over 2i integral of e to the iz over z dz minus e to the minus integral of e to the minus iz over z dz, right? That's not actually exactly equal to f of z here, the integrand in this one. So we can apply a substitution to make it look similar, right? If we substitute in so here's our first one. If we substitute in z equaling to minus w, right, then we will actually end up with e to the minus I w over w dw, right? Except here the boundary will be reversed, right? So if our integral was from, say, a to b, then this one would be from a to b, this one would be from a to b, this one would be from a to b, this one from a to b, but this one would be from the negative of those, right? From negative b to negative a, right? Due to our substitution. But now finally we've got our desired integral in terms of our function f of z, right? So perhaps we could relate these two integrals somehow to the theorems that we've learned, attempt to simplify them somehow. So if we observe what those integration paths look like on the complex plane, right? The path from a to b along the real line would be in this direction, right? The path from negative b to negative a would be also along the real line in this direction, right? And our function f of z has a singularity here, right? It's not holomorphic here at the origin because that's when the denominator equals to 0, so we'll just mark that with an open point. Perhaps attempting to apply Cauchy-Goursat, we want to find a contour that includes these two segments, right? That would evaluate to 0, right? Via the Cauchy-Goursat theorem. So that would mean that we have to find a contour along which the function is holomorphic and inside which the function is holomorphic. What it basically means is that we have to avoid this point here, maybe with a semicircle like this, traverse in this direction, and loop back to our starting point with a big semicircle like this, perhaps, right? And we know that because our function is holomorphic along this big contour and inside that contour, then the integral along this contour has to be equal to 0 via Cauchy-Goursat, right? So finally we have an expression relating these two integrals, right? And hence putting a number to the integral that we want to determine. So now our task is just to determine, right, what this semicircle integral is going to equal to and what this semicircle integral is going to equal to, right? Because they are part of this sum that equals to 0. So let's see how we actually go about this. So here, our bounds we've set to be epsilon and r, right? Epsilon and r. We're not plugging in 0 and infinity just yet because that's actually, we're going to have to do that at the end when we push epsilon to 0 and r to infinity, right? For now, if we want to actually have this contour across which we can apply Cauchy-Goursat, we need them to be, real numbers. So here's the contour that we've created, that's along which the integral is equal to 0, right? And it separates into these 4 integrals, right? These first two, are the ones that sum together to form an expression that looks like the integral of sine x over x. And these two are the ones that we need to evaluate, right? So, where we evaluate the first one, right? The small semicircle, it's along this semicircle contour little gamma, right? And it's equal to, negative of that integral, but traverse backwards, so from 0 to pi. And when we integrate this, we get the integral of this expression, right? E to the I epsilon EIT. But remember, we want to push epsilon to 0 because our integral is from 0 to infinity. So as we push epsilon to 0, this integral is going to tend towards minus I integral from 0 to pi of e to the 0 dz, right? Which is just the integral of 1 dz from 0 to pi, which evaluates to minus I pi. All right, so that's one of the two integrals we need to evaluate done. And the second one is going to be a little trickier. We evaluate it and obtain this expression, right? Which is pretty opaque when it's still in terms of big R, right? But you may have a suspicion that this expression actually goes to 0 as R goes to infinity. And the way that you actually prove this is you use the ML trick that we used before, right? So the absolute value of this integral is going to be smaller than or equal to the integral of the integral of the modulus of the integrand, right? The modulus of I, EIR, EIT, right? And when you evaluate this, it evaluates to be e to the minus r sine t dt, right? In the modulus function. And as you push r to infinity, which is what we want since our upper bound is infinity, this is going to tend towards the integral of 0 from 0 to pi, which is obviously just 0, right? So our second integral that we need to evaluate is just equal to 0. Finally, that means that we know that this sum, right, so the integral across the entire contour, is equal to 0. And furthermore, that when we push r to infinity and epsilon to 0, two of those integrals are going to evaluate to minus I pi plus 0. While these two integrals, right, the ones that we identified before along the two paths, are going to sum together to equal the integral that we want. So finally, wrapping things up, we've got these two sum together equaling I pi, right? And when we actually combine them, we see that the sum of the integrand is e to the ix minus e to the minus ix over x, which is 2i times sine x over x. So we get that 2i times the integral that we want from 0 to infinity of sine x over x dx is equal to I pi. And finally, dividing through, we get that the integral from 0 to infinity of sine x over x is pi over 2. Quite a long question, and it required us to apply everything that we needed, but I hope it's a good example of the type of things that we might have to do in the exam. All right, thank you for listening, and that's the end of the seminar.